In point estimation, there's often a great focus on estimators that are unbiased. Now, the unbiasedness of an estimator does not necessarily make it a good estimator. Typically, we're thinking about bias trading off with variance, and so we want to be considering the MSE of an estimator. However, unbiased estimators are typically quite useful, and so it makes sense to pay a little bit more attention to unbiased estimators in particular. And so there's a few key realizations to make when we're dealing with unbiased estimators. And the primary one is that if you have two unbiased estimators, then really the only way that we're going to be comparing them is through their variance. So the sort of central idea here is that if you have an unbiased estimator, so among the unbiased estimators, the MSE is going to be equal to the variance of the estimator, right? And we can see that because we know that the MSE of an estimator, right, so the MSE is equal to the bias squared plus the variance, right? And so based on this formula, we know that if the bias is equal to 0, then it goes away, and we have the MSE equaling the variance. And so because of this, unbiased estimators are kind of interesting to study in their own right. Okay, so we can consider that sort of more deeply. When we want to try to select a good estimator for any population parameter, it's always natural to see if we can first find an unbiased estimator. Because if an unbiased estimator exists, then it's a very natural starting point to choosing or selecting a good estimator. Now, if an estimator is unbiased, the variance and MSE are equal, right? We saw this on the previous slide. So the MSE is equal to the bias squared plus the variance. If they're unbiased, the bias is 0, so then it's 0 plus the variance. So the MSE and the variance are equal. And so if we're only considering unbiased estimators, then the best estimator is going to be the one with the minimum variance, right? This leads us to considering what we call the minimum variance unbiased estimator, or MVUE. Okay, so fortunately, the name here is quite descriptive. The MVUE is going to be the unbiased estimator that has the minimum variance among all possible unbiased estimators. Okay, so if it has the smallest possible variance and it's unbiased, then it's an MVUE. If it is not unbiased, it can't possibly be the minimum variance unbiased estimator. And if it doesn't have the smallest possible variance, then it also can't be the MVUE. Okay, so the MVUE is the unbiased estimator for some parameter that has the minimum possible variance among all unbiased estimators for that parameter. So in a sense, it's going to be the best possible unbiased estimator. It will have be the unbiased estimator with the smallest possible MSE. Okay. So why are MVUEs useful? Well, if an MVUE exists, it's typically going to perform well, right? We know it's unbiased, which is desirable, and we know it has the smallest variance among unbiased estimators. That's also going to be desirable. There's also a great deal of more advanced statistical theory dealing with MVUEs. So if you can find an unbiased estimator, typically you can turn that into the MVUE, right? So if an unbiased estimator exists, it's not typically that challenging, though it requires a lot of complex statistical machinery to find the MVUE from there. And so because of that, not only can we know that they're going to perform fairly well, or at least typically they'll perform fairly well, it's also very possible to actually find these estimators, which is quite nice. Many commonly applied estimators are actually minimum variance unbiased estimators. So for example, the sample mean is the MVUE if the population is normally distributed. So if we have a normal distribution, then the sample mean is going to be the MVUE. The sample mean is always an unbiased estimator, but for some distributions, it's not going to be the minimum variance unbiased estimator. The sample variance is the MVUE if the population is normally distributed. Right, so among all unbiased estimators for the population variance in a normal population, the sample variance is going to give you the smallest overall variance, and so then that's going to be the MVUE. The sample standard deviation is not the MVUE if the population is normally distributed. Right? So it's worth thinking about, why is this the case? Well, the sample standard deviation is not actually unbiased for the parameter, right? And so even though the sample standard deviation is a very reasonable estimator, it's not an unbiased estimator, and so therefore it can't be the MVUE. Okay. When they exist, MVUEs are good estimators. Now, that is to say, they won't always exist. But when they do, they typically are going to perform quite well, right? It's not even guaranteed that we'll ever be able to find an unbiased estimator in any given situation, and so certainly we're not always going to be able to find the MVUE. But if we can, they're going to be well-performing estimators. Now, a key point here is that even if the MVUE exists, that does not mean it's going to be the optimal estimator in terms of the MSE. It is possible that we can find a biased estimator that has a lower overall MSE, a biased estimator that is actually preferable in terms of the MSE selection criteria. Right? So just because you have a MVUE does not mean it's the best possible estimator. However, it's always going to be a fairly reasonable estimator to at least start with. So overall, the MVUE provides a useful starting point and will typically result in perform an estimator whenever they exist. Right? It gives us an unbiased estimator, which we like, and among all of the unbiased estimators, because the MSE then equals the variance, the smallest variance is the best estimator that we have in that class. Right? And so if you're only thinking about unbiased estimators, you really want to be trying to find the MVUE. And otherwise, there might be estimators that perform better, but those estimators are guaranteed to have a bias with them. So whether that's a useful trade-off or not is going to depend on the specific context.